your topics in 10 years when you will gain most of your skills. So for that reason, I try to every year try to ask one question, right? So what could be another perspective to look in our domain, in data science and artificial intelligence and in machine learning. So this year, I decided to make emphasis on causation. So all of you guys probably knows that this statement, correlation does not imply causation. And we studied this during statistic classes, but does it? So last year, I became familiar with this book, The Book of Why, from Judah Pirro, and I highly recommend this book. And so basically, the motivation for this book, as far as I understand it, and I think that Sebastian could correct me if I'm wrong, that the statistics and data science that built on top of statistics and modern approaches in artificial intelligence that built on top of that again, mainly looks on correlation, right? So we have a bunch of data and we try to bring correlations from them. But we human beings are mostly interested not in correlations, but on causation. So we are like all of our life, how we live our lives and how we behave in environment. It's mostly about causation. So our brain, as a neuroscientist proved it already, we are oriented to make this causation causal links. And how about causation? How can we infer causation? And this is a keynote talk for today. And also we will have a short course from Margarita, as I mentioned, on causal learning. So I asked Sebastian to join us. He's a postdoc at Copenhagen Causality Lab, one of the center in Europe and I believe worldwide on causality. This lab is located in Department of Mathematical Sciences, University of Copenhagen. So Sebastian got his PhD at Max Planck Institute for Intelligent Systems and also in ETH Zurich. And previously he got his master degree in computational statistics and machine learning from University College London. So that's basically it, short introduction. I bet that you, Sebastian, can tell much more about yourself, about your past, and about your research lab. And I think it would be interesting for participants of our summer school. So please, the floor is yours. Thank you.
Thank you very much. I'm just gonna pull up the slides real quick. I hope you can see the slides now. Thank you very much for this kind invitation and also for this kind introduction. I'm very pleased to have extra screen time for causal inference right at the outset of a data science summer school. So in recent years, it has become a popular topic. Also, if you look at the big machine learning venues like NeurIPS, ICML, ICLR, you will find a lot of papers now kind of revolve around the theme also of causality. So I'm extra happy that we have it right at the outset. And maybe I will take this chance basically to kind of sketch why there's this slogan, correlation does not imply causation, why we should be caring about causation as data scientists. And maybe you can just take this throughout the summer school and every now and then maybe pause and then ask yourself, so what have we learned? Is that a causal insight? Is it a predictive insight? How does causality play into this? Or don't we even need a causal tool for this particular question that we're trying to answer? I will put up the slides later and you will also find it on my website, on my Twitter. And before we jump right in, I wanna, but it was already done now, I'll just repeat this. I wanna encourage you to participate in the causality sessions Wednesday this week. So you will have the chance to learn much more about causality than we can cover in this 1 hour talk, where I will mostly focus on the motivation and the kind of idea, the conceptual idea that you maybe should be keeping in mind and that could be helpful throughout, but you will learn much more in this causality workshop on Wednesday. And then I also added a slide. So basically, depending on how much you want to dive into causality, there's 8 hours, 4 hours, and 2-3 hours lectures online that I find really helpful to get started. I will also add maybe some references later for some starting points in the literature, but videos is also a good starting point. So enough of advertisement, only briefly about the Copenhagen Causality Lab. I decided to basically scan all the papers. I used the scimeter.org, and I wanted to show you this word cloud to kind of orient ourselves in this like grand field of machine learning, like what themes are interesting to a causality researcher. So you see very central. I'm very happy that it actually automatically realized that we're working on causal inference. So that's quite central, of course. And right off on top of this, you see intervention. This will be a central term when we talk about causality. Basically, this is the key question that we're asking here is, can we also predict what will happen to our system that we're currently modeling once we intervene, once we go in and change something in the world around us? This also nicely relates to the motivation that we've just heard. Like, we as humans, we interact with the world. So we need to predict what happens once I pull this lever or once I kick this box over here. It's also quite a central concept. We will learn this later. There's conditional independence. So you see, this is kind of leaning towards the classical statistics literature. There's non-parametric. We have finite mixtures of things. We have a likelihood estimator. So there's a lot of statistical concepts, but causality is something more than statistical concepts. So we're trying to kind of link and find assumptions that make us, that allow us to kind of infer something about causality from statistical properties alone. Why is this maybe a debated question to tackle even? So if we go 100 years back roughly, there's this kind of infamous statement by Bertrand Russell that I'll just read out. All philosophers of every school imagine that causation is one of the fundamental axioms of postulates of science. Yet, oddly enough, in advanced sciences, such as gravitational astronomy, the word cause never occurs. To me, it seems that the reason why physics has ceased to look for causes is that, in fact, there are no such things. The law of causality, I believe, like much that passes muster among philosophers, is a relic of a bygone age, surviving like the monarchy only because it is erroneously supposed to do no harm. So here you see 100 years back, a very, very strong argument against causation. Like Bertrand Russell even takes it to a point where it says there's no such thing as a cause and it never occurs. And like the advanced sciences, they wouldn't even dare to do this. Now, 100 years later, we see this quite differently. We know that it's a concept that we should be caring about. And also the slogan, correlation does not imply causation, I will convince you hopefully throughout this talk that you need to take this with a bit of grain of salt. There's a good reason why there's this slogan, because you cannot just simply take correlation for causation, but correlation will still tell us something about causation. So quick fast forward, Julia Pearl in 2009 in his book Causality. Fortunately, very few physicists paid attention to Russell's enigma. They continued to write equations in the office and talk cause-effect in the cafeteria. With astonishing success, they smashed the atom, invented the transistor and the laser. The same is true for engineering. So Julia Pearl is one of the key figures in this kind of movement, and he formalized the causality framework to make it kind of amenable to statisticians and data scientists. And indeed, we want to learn something about causality quite often. And you can see that the last 100 years, quite something has happened from kind of abandoning causation as a concept overall. And then now we're kind of focusing, and if you check out the recent machine learning literature, we really like, there's a huge push towards causal concepts and causal learning. Causal questions require causal answers. And I think this is my key motivation. And it sounds like a very kind of subtle or maybe even simple, naive statement. But this is the key motivation to do causality. If you ask a causal question, then you need a causal answer. So there's no way around this. And if we as statisticians were classically trained, we probably have heard the slogan, correlation does not imply causation. And then there's two ways out. You could either stop and say, okay, well, then we don't even do and try to do causal inference. And then there's another approach that I'm trying to convince you of today. You should actually take this challenge, and it's super challenging to infer causality from data. But if we are seeking answers to causal questions, then this is the only way we can go. So maybe let's give an example of some failed inferences and why there's this slogan. So you see here 2 news articles from 2013. On the left-hand side, you see eating chocolate produces Nobel Prize winners, says study. We will see on the next slide, there's indeed a Nature Communication study where there was a strong correlation between chocolate consumption and Nobel Prize winners. And you've seen here in this heading, in this headline, it's basically been turned into a causal statement. If you eat more chocolate as a country, you produce more Nobel Prize winners. On the right-hand side, it's kind of twisted again, this statement. You see geniuses are more likely to eat lots of chocolate. So here it's kind of the other way around. The statement is if you're a country with many Nobel Prize winners, maybe those are the geniuses, and they are much more likely to eat lots of chocolate. So this is maybe why you see Nobel Prize winners and chocolate consumption to be positively correlated. So let's back up this statement and look into this study that has been done. So you see here a plot. On the x-axis, you see the chocolate consumption per capita, and on the y-axis, you see the Nobel Prize winners per 10 million population, and you see basically different countries placed on this scatter plot. And as you can see, and it's also marked in the left corner here, it's a very strong positive correlation. So countries that exhibit larger chocolate consumption are also countries apparently that produce more Nobel Prize winners. And we've seen that such a correlation, so descriptive statistics of this plot is to compute the correlation coefficient. Here it's 0.09. It can be interpreted, or maybe it's even very tempting to conclude some causal relationship must be at the root of this correlation. I want to convince you now that this is dangerous to do. This is why we have this slogan, correlation does not imply causation. But I want to do this by contrasting 2 concepts. We will call one concept seeing, which will relate to classical conditional probabilities. And the other concept is doing, where we compute probabilities or the system once we have intervened in the system. So let's imagine the following story. So we know about this strong correlation, and then we can ask ourselves, okay, now if Kim goes on a cruise to another country, then he could just see how much chocolate is consumed, and he could report this back to his lab mates, and they could kind of place this country on this plot. So let's say he travels to some country that consumes X amounts of chocolate. Then if they want to predict, okay, how many Nobel Prize winners are we expecting from the country, it's very likely that you would place them somewhere around this kind of diagonal line here in this correlation scatter plot. This is a very valid prediction you can make because these data have been observed. So you have the data points we have already is just observing how much chocolate has been consumed and just observing how many Nobel Prize winners we've seen from a country. So if Kim just reports back the chocolate consumption not intervening in any way, then indeed there's a good prediction to use the strong correlation that we have seen. If instead Kim takes a bunch of chocolate jars and basically feeds a country with enormous amounts of chocolate for a year, then he's doing something different. He's kind of enforcing a certain amount of chocolate consumption, or he is at least changing actively how much chocolate is consumed in a given country. Then we can again ask, okay, can we now predict how many Nobel Prize winners we should be expecting? And the takeaway here is that this is conceptually 2 different questions. One is a seeing question. So we have observed for a bunch of countries already how chocolate consumption and Nobel Prize winners correlate to one another. Probably we can just place another observation on this plot and is a rather good prediction. The other one is doing, if we actually go in and change the system, we change the country, we induce a higher chocolate consumption, then this may be or may not be an entirely different distribution. So for example, you could ask yourself, what would happen if we feed the French with much more chocolate, would we produce more Nobel Prize winners? Well, I guess a lot of us wouldn't expect this to happen. There's other possible explanations for the strong correlation. One is, for example, the economic growth and economic wealth of a country. There could be other factors that explain both a higher chocolate consumption and a higher number of Nobel Prize winners. So the question is, can we predict the number of countries' Nobel laureates? And it's two different questions depending on whether we just observe the chocolate consumption or whether we actually go in and do something and change the chocolate consumption. And this is kind of the turning point where you see, if you interpret the seeing correlation, so the correlation plot that we've observed here already, if you use this to predict also what will happen once you go in and bring lots of chocolate, then this is where your causal inference fails. This is where this whole slogan is very apt to warn you, well, you shouldn't be doing this because correlation does not per se imply causation. So up to this point, I hope I have convinced you that, well, if we ask causal questions, we need causal answers, but disappointing news. Indeed, in some sense, correlation does not imply causation. That's a bit sad, and this is also what we saw in Julia Pearl's quote early on. If we just stop there, which is kind of what Russell's standpoint was, then you won't ever answer causal questions. So maybe we should be looking for ways to infer something about causation from data in some way. And I want to convince you on the next few slides that indeed correlation may tell us something about causation, and the whole causal inference machinery is about formalizing how exactly we can learn causation from correlation. So how we should be starting this, maybe one nice example is we look at a two variable scatter plot. So instead of chocolate consumption and Nobel Prize winners, now we have a Y variable and a Z variable. And I've tilted this plot intentionally to kind of disambiguate and kind of, I want to not bias you towards any inference about whether Z causes Y or Y causes Z just from what variable I place on the x-axis. So this is why we're looking at this in this 45-degree turned way. Now we could ask ourselves, well, this could be any data points, two variables Y and Z, and we could ask ourselves, and maybe I asked you also to think about this right now. What would you guess? If you have one guess, what would you bet on? Should Y be causing Z or should Z be causing Y? And we've just learned correlation does not imply causation. So we see a strong correlation here. But maybe there's something about this plot that gives it away, or that gives us some hint about what variable we should be expect to be the cause and which one we should expect to be the effect. Since we're now in this online setting, I'll just reveal the solution to you, and we will see a second example shortly. And I will try to explain how you could maybe kind of see this from the scatter plot. And we're now in an early stage. I want to convince you that from data, you may be able to infer causation, but it will require us to make assumptions. So here I will reveal now the true identity of these variables. So on the Z variable, that was the temperature of a location on Earth. So you see it's the average yearly temperature, and here the big chunk is between 8 degrees Celsius and 10 degrees Celsius. And on the Y variable, we have the altitude of a location. So you see on the right outset of this plot, 3,000 meters, that's probably the Zugspitze, a high mountain in the Alps, and it has an average temperature of somewhere between -4 degrees Celsius. And as you go lower in altitude, the average temperature increases. This is what we're seeing here. So there's a huge increase in temperature as we go lower in altitude. But then on this lower end, you see this funny kind of U-shape or inverted U-shape twist here. So there's a certain point where when we go even lower than this, then temperatures start to fall again. The reason for this could be as you move to basically zero altitude, you're moving closer to the sea where there's more wind, where you're more exposed to rough weather conditions. So the average yearly temperature will be lower again. So here we would conclude, okay, changing the altitude of a city would probably change the temperature. As you move up the hill, you can expect an average temperature that is smaller than if you're basically somewhere in the Midlands. But how can we tell without knowing what these variables are? How could we tell from such a scatter plot which way around the causation should go? Here, maybe there's one key point to look at that could reveal something, namely if you kind of take a slice of this plot at 8 degrees Celsius average temperature, you would see that there will be kind of two hubs. It will be a bimodal distribution. We will have some cities that are at a very, very low altitude. Then there's a certain range where there's no city with an average temperature of 8 degrees Celsius. And then if we go even higher in altitude, then again, we will see a bunch of cities with such an altitude and such an average yearly temperature of 8 degrees Celsius. If now the causation was the other way around, so let's for a moment imagine Z was actually the cause, then that would be a really troubling kind of interpretation for us. That would mean, okay, if we set the Z variable to 8, then it could either happen you fall between 0 and maybe 50 meters, or you could fall between 400 and 500 meters. Whereas if you set it to 10, then you're only in a unimodal distribution and you would only end up kind of between maybe 100 and 200 meters altitude. So this is really difficult for me to formalize and verbalize in words. And the whole benefit of a formal causal inference framework will be to have very precise, formally precise notions and assumptions that make causal inference work. In this plot, I maybe want to give you an idea that there's something to be learned from correlations or even just from scatter plots and noise distributions and how they're shaped. Let's see another one maybe of these examples. So again, two variables, a Q variable and a W variable. Again, we don't know which way around the causation goes. If we just look at this data, it could be any two variables in your data that you're interested in. There's something about this plot that gives away somehow which direction is more plausible for a causal model. I will reveal this. We have now on the left axis, we have the solar radiation, and on the right axis, we have temperature. So the more solar radiation, the higher the temperature. This is what we're seeing up in this plot. And down here, we see the lower the solar radiation, the lower also the temperature. How could we infer that it must be W causing Q instead of Q causing W? Well, if again, we take this approach where we look at the distribution as we take certain slices of this plot, you will realize if you were to consider a slice in this plot where you consider temperatures of 10 minus 10, you would see that this would be a distribution with support somewhat between 0 and 3000. So kind of this line segment here that I'm following now with a mouse cursor. Whereas if you were to move up the temperature and go up here, you would realize that the support doesn't even cover these early ranges here, and then suddenly has a much, much wider support for higher solar radiations between 4,000 and up to 10,000. The nice thing is, if you turn the roles upside down and you consider how it is indeed the case that W is a cause of Q, then you see that the support roughly as you follow this cloud and you take now line segments in this direction, so cutting through this kind of cloud point of clouds, you will realize that the support is roughly the same and kind of shrinks a bit as you move higher up here, but it's much more homogeneous than if you were to flip the roles of Q and W. So something about this plot could maybe tell us something about causation. And it will be, the art will be to formalize this so that we could, instead of arguing about this scatter plot and doing some hand-wavy explanations, that instead we could agree on some set of assumptions, and then given those assumptions, we would all agree on what should be the cause and what should be the effect. So maybe correlations tell us something about causation, and now let's see how this should work out. And this is basically what we're trying to do with causal inference. We're trying to find a set of assumptions that make very explicit how we can, in a very principled algorithmic way, move from data to an inference about causation. Here you see, this is again from Perl, is a very good example of what's the problem and what's kind of missing for us to make it work. Causation is a programmer's nightmare. So as input, we have two conditionals, basically. If the grass is wet, then it rained. And if we break this bottle, then the grass will get wet. You could conclude, if we break this bottle, the grass will get wet. If the grass is wet, then it rained. So in short, if we break this bottle, then it rained, which is obviously not what we would like to output. And how could we kind of disentangle this or kind of avoid this problem? And this is kind of one key invention that we need, is we need to have an algebra of doing. This is how Pearl called it here. In classical statistics, we have conditional probabilities. So we know, we can ask ourselves, what's the probability that it rained, given that we see that the grass is wet? On the right-hand side, you also see that this is basically rewritten with a Bayes rule. So this is classical statistics, but it's only the algebra of seeing. What we're missing is some notion to designate what happens when we make the grass wet. So this is when we break the bottle. This is on the bottom of this slide. Now you see just a new notation to start with. Basically, what happens with the probability of rain, given that we do intentionally go in and we intervene and we make the grass wet. Well, this is obviously not the same probability as the probability up here, where we just observe, okay, we look outside the window, grass is wet, probably it has rained. Whereas here, if we just intentionally water the grass with a bottle, then this doesn't really tell us anything about the probability that it rained. And it is also indicated on the right-hand side. This is just merely then the probability that it rained without even taking into account the wetness of the grass beforehand. So this seems maybe a bit subtle here, but it's really, this is one of the key ingredients to be able to distinctly talk about seeing, so classical conditional probabilities versus doing, that is probabilities that are different once we intervene, when we go in and make the grass wet, is something different entirely than just observing whether the grass is wet by kind of natural causes and rain. So here you see this now a bit more formally. The idea is we first need to equip our kind of syntactic toolbox with two different notions. One is for conditional probability. So here it's called observational probabilities, because this is just when observing the system, you just realize, okay, the grass is wet. What is now the probability of Y, given that we've seen X taking on the value X? And this may be or may not be a different distribution than asking yourself, okay, what happens if I actually go in and set X to a certain value? And we will just denote this by do. So we do an intervention and we set X to the value X. And it will turn out that these two distinctions are kind of at the heart of why there's the slogan correlation doesn't imply causation. This is whenever you kind of mix up the two. In our country example, it's basically feeding chocolate is the do intervention, and just observing how much chocolate is being consumed in a country, that's just the classical observational probability. And if you just want to predict this conditional probability here, then you're fine using your data and placing your country on this positively correlated scatter plot slope. If you actually feed countries with more chocolate, or you prohibit chocolate in a country, then you're not quite sure without further assumptions what you would expect for the number of Nobel Prize winners. So this is why we need this distinction. I will now kind of give you a high level intuition about why a causal model is something different than what I call here normal probabilistic or classical probabilistic model. So you will learn a lot throughout these 2 weeks about the left-hand side of this plot. And from time to time, maybe think also about the right-hand side plot. On the left-hand side plot, you see what we kind of do in classical statistics. So I called here a model M over variables X. And what it basically is, it's a parameterized, so theta are parameters, and P of theta is a distribution, and it kind of assigns to each set of parameters a different distribution. So you could think of a regression model, and then as you change the intercept or the slope, you will get a different distribution that this kind of model entails. And on this lower plot, you see kind of an illustration, or how you could maybe think about this is the space of all distributions. Now we fix a model which is kind of fixing one line, one subset of possible distributions. And then as we change the parameters of our model, we will just move the distribution along this line. So we're talking basically about one distribution. On the right-hand side, you see an intuition that may be helpful to think about a causal model as a set of distributions. So now we have mx maps each parameter to a set of distributions. And this set of distribution is indexed by these I, in this IX set. And this is a set of interventions. So this is basically where this term comes in. And in the next slide, we will see what this could correspond to. But you could think about a causal model as being a set of distributions, and they are indexed by different interventions. So you could say, okay, this is the distribution I expect once I break the glass. This is the intervention, the distribution I expect once I don't do anything. This is kind of the null intervention or the observational setting, which is also what we do on the left-hand side. But then we have these additional kind of 3 distributions that we're all modeling at the same time. So we're talking about a set of distributions and modeling all of them at the same time. So if you ask yourself, what is a classical graphical model and how is it different from a causal model? A graphical model only kind of claims to model this observational distribution well. A causal model ideally also gives you a prescription. Okay, and now you've got the observational distribution, you need to change this and this if you're asking yourself about what happens under interventions to the system. Let's look at an example or depict an example here. Now we have 4 distributions. The observational distribution here. So this is how do maybe countries, chocolate consumption and Nobel Prize winners evolve naturally in the world. And then this could be, okay, what happens if we set chocolate consumption to 0? So if we go in and prohibit chocolate in a country, and then you can think about stories, what A could correspond to, and ask yourself, what happens when I set A to 0 and C to 0? So we will denote these 4 distributions with an upper script that kind of tells us, okay, this is the observational distribution. This is the distribution once we set the chocolate consumption to 0. This is the distribution once we set A to 0 or A and C to 0. So we're modeling several distributions at the same time, and these different distributions correspond to interventions. So we can ask questions now, what happens if we intervene? Then we know, okay, we need to jump to this distribution, and this is how the data will kind of evolve once we set chocolate consumption to 0. I want to also at this point hint at the ordering of this. So what I've done here, I've added arrows between the observational distribution. This is just observing the system unchanged, but we could also go in and set A to 0. If additionally we also set C to 0, then we would be moving up here. So this is kind of the interventions are kind of, we can equip them with an ordering structure. And of course the model thus is a poset, so partially ordered set of distributions. I think the key takeaway here is a causal model is more than a classical statistical model. A classical statistical model models 1 distribution, and now we're modeling several distributions, but we're also modeling how we move between those distributions. To give you one example, and this is like one of the terms you will often hear, is a structural causal model or a structural equation model. And you could view this, so I'm focusing here on the intuition, but now we're also writing down one structural causal model, and you could view this as one way to write down a causal model. So instead of basically listing a bunch of distributions and how they relate to one another, I want to maybe have a more succinct description of this. And one way to do such a description is a structural causal model. So we will say a structural causal model M over variables X needs to have structural equations. So I'll just write down a very simple 2-variable example here. So we could say the X1 variable is just a noise term E1, and the X2 variable is X1 plus E2. Then we need to have interventions. Let's consider 3 interventions. No intervention, which is the observational setting, X1 setting to 5 and X2 setting to 3. And then we need to specify, this is what this last item in this triplet is, we need to specify what is the noise distributions. And I motivated the structural causal model by the idea that it's a way to describe several distributions, so it's a causal model, at the same time in a succinct way. If we basically just use the equations and the noise distributions, we will realize that this implies a distribution on X1 and X2. Namely, X1 will be a standard Gaussian, and X2, since it's the sum of X1 and E2, it will be a Gaussian with double the variance because it kind of enters X1 and E2. And now it's a succinct way to describe several distributions. So now we can also consider the distribution under intervention x1 equals 5. How do we do this? Formally, we basically just need to agree, okay, how do we obtain the distribution corresponding to this intervention? You take this equation and you replace it by x1 equals 5. And then you ask yourself what distribution is implied by this model then. We will realize that then x1 will obviously just be a constant 5 because we've went into our system and set x1 to a fixed 5. And the distribution of x1 will now be lower variance because the variance now is only due to E2. And x1 is a constant 5, so we have a mean shift of x2 to a mean of 5. So this is how a structural causal model induces several distributions. On the right-hand side now, we can also ask ourselves about the distribution once we intervene on x2 and set it to the value of 3. Maybe here's also a good point to realize that this there's an asymmetry between intervening on x1 and intervening on x2. You see on the bottom row here, in the observational setting, x2 has this distribution. It's distributed around 0 with variance 2, whereas in the interventional setting, when we intervene on x1, the mean and the variance changes. So we could say x1 is a cause of x2, because once we intervene on x1, it changes what x2 looks like. Whereas if you take the right, the intervention on x2, you realize that the distribution of x1 is the same as in the observational setting. So fiddling around with and changing x2 doesn't at all change how x1 looks like. So here you see this asymmetry, which is not reflected in a classical correlation, which is just symmetric, but a causation is anti-symmetric, is asymmetric. There is some cause and some effect, and intervening on one, namely the cause, changes the effect, but not vice versa. So now we've learned basically kind of an intuition. A causal model is a set of distributions. Here we've seen a way to write down a causal model. Now we can ask ourselves, okay, so what is this whole causal discovery about? And I like to kind of use the following image to explain this kind of in a more intuitive way, maybe. So causal discovery has the following goal. You're given observations. So on the left-hand side, let's assume we're given observations of the system unintervened. So in the observational distribution, we just observe maybe the grass and the wetness throughout the year. And then we could also ask ourselves, okay, what happens if we break a glass every second day? How does the distribution now look like? Let's say we're given data only of those two distributions. And then the aim of causal discovery is to write down a causal model. But now the causal model will also tell us something about what happens if we do intervention I3, what happens if we do intervention I2. So we're kind of trying to learn something about these other distributions that we have not yet observed. And this is a very hard task, obviously. And in the next slide, I want to convince you that without further assumptions, it will not be possible to do this in a meaningful way. And this is, again, why there's the slogan, correlation does not imply causation. It's very tough. And if you just take correlational results and interpret them kind of naively as causal statements, you will often be misled. So what I've done here is I've basically modeled the same observational distribution. So you see in all of three columns, I've put down the px null. So this is the observational distribution. It will always be the same observational distribution, and it's described by 3 different sets of equations. So after this lecture, if you doubt this, you can basically convince yourself that for NA, NB, and NC just being standard Gaussian noise, these 3 different descriptions will result in the very same observational distribution. I've up here also depicted visually what this graph would correspond to. So as you can see, in this middle one, we would be saying B is an effect of A and C, whereas on the left-hand side, B would be the cause of A and of C, and C would also be the cause of A. So kind of causally, we can already here see that this looks very different. I've also kind of depicted this in these distribution plots. So this causal model induces the same observational distribution as all these other 2 models here. But if we now start replacing equations, which corresponds to modeling interventional distributions, we will realize that the interventional distributions, so here denoted by those three dots in this plot, will be different from the ones implied by this model, which again will be different from the ones implied by this distribution. So on this slide, there are shown three structural causal models that all induce the same observational distribution, but they disagree on the interventional distributions. So if we now were to go out and observe data in the observational setting and basically find a model that very well fits this observational data, we could take either of these three models. It wouldn't matter. We couldn't distinguish them based on our observational data. But the implications they have for how they predict interventional distributions, they basically completely differently describe what happens to the system under interventions. So this is basically saying if you model the observational distribution, let's say using this, you will do equally well than using the left-hand side model. But if you now ask yourself what happens if I intervene on C, set it to 0, those two models will give you vastly or possibly vastly different answers about this question. So you cannot use this model to answer causal questions. You can use it to model the observational data, but not to answer causal questions. And this is one of the main reasons that fitting observational data well, so taking any observational data and fitting it by a structural causal model, this on its own is not enough. We need some further assumptions to decide, okay, which of the three is now the more plausible causal model that we should use to predict what happens under intervention I3. For this, we kind of equip our inference machinery with further assumption. And this is a very crucial point, and I'll just repeat this to make it absolutely clear. If you don't make any further assumptions about how causality manifests itself in statistical properties, then there's no way for you to infer causality from correlation or from statistical properties. So this is why, per se, this slogan is very valid and very apt, that correlation does not imply causation, and we need to do some extra work and we need to put in extra assumptions to make this work. And one is the so-called Reichenbach's principle of common cause, and it is kind of intuitive. If you observe two variables to be dependent, so you observe somehow that X and Y are, let's say, positively correlated, then we say, well, then either of the following three must be true. Either X is a cause of Y, or there is some other variable set that is a cause of X and of Y, or Y is the cause of X. Because otherwise we wouldn't expect just two independent variables. They are independent. So if we observe a dependence, then there must be some causal explanation for this dependence. This is what this principle says, and this is one way kind of to move forward and say, well, statistical dependencies and independencies do indeed tell us something about causation. But this is basically something that we kind of, we agree on this to be true. Whenever we see variables to be dependent, then one of those three cases needs to be true. They could also occur simultaneously. And then a key problem is that we cannot easily distinguish between those three settings. If we just observe three variables to be dependent, we need to accept that it could be either of the three cases. So this could be chocolate consumption causing Nobel Prize winners, or chocolate consumption being caused by Nobel Prize winners, or this could be economic wealth causing higher chocolate consumption and causing higher number of Nobel Prize winners. And for this story that I put forward, of course, we have kind of an idea of what should be the true causal structure behind the dependence that we observe. But if it's two variables where we try to infer causation from data, then we have no prior maybe on how, like, what is the more plausible explanation between the three, and then we need to accept that it could be either of the three. We can now move forward and say, okay, a functional model of causality is basically you model each variable, so the effect xj, as a function of its parents, and when we observe all kind of what there is, then these noise terms become statistically independent. And we can now ask ourselves, what happens if we truly believe the data is generated according to such a model? Which properties of the joint distribution follow, and how can we maybe leverage this to go back from statistical properties in the data to causal structure? It turns out there's kind of easy consequences when you assume your system is indeed governed by a functional model. Then these 4 properties turn out to be equivalent. So maybe the kind of most intuitive at this point is the local Markov condition, and it says if indeed your data and your system is governed by a functional model, so a effect variable is always a function of its causal parents, of its causes, then you can also conclude that every node is conditionally dependent of its non-descendants given its parents. So let's zoom in here on xj. The statement says if we now condition on the parents, which is these red ones, then the blue values, the non-descendants, don't tell us anything more about xj. We've already observed the direct causes of xj. Then knowing these blue guys here doesn't tell us anything more about xj. So the takeaway here is if you believe your model to be kind of stemming and modeled or being generated by a functional causal model, then this property is true. Indeed, if you were to condition on the parents, you would find that there's a conditional independence. Here's a metaphor for this that I will skip, but I want to explain how you could use this now to infer causation from data. For this, let's do a 3-variable example. You're given observations now, W, E, and S. I put a bike here in brackets to kind of indicate that I have kind of a toy story behind this simulated data, where S is the cycle speed. And we can ask ourselves, what is the causal structure between S, W, and E, having observed the following data? So here you see 3 scatter plots, W and S, E and S, and E and W. And now we can ask ourselves, okay, how should we now even move to any conclusion about the causality between those variables? We will do this by the following 4-step procedure. We will first ask ourselves, okay, which variable pairs are dependent, or correlated, or independent, uncorrelated? The second step is then we will assume that indeed behind our data there is the data generating process is a functional model. If we assume this, then we know that this Markov condition holds true, for example. Then we will list all causal structures that are possible. And by possible here, I mean in the step 1, we have kind of investigated which variable pairs are independent or dependent. So this will constrain and restrict the set of possible causal structures that could explain such data dependencies. And then we will ask ourselves, okay, is there any further assumptions we can make to narrow this selection down? Okay, let's do step 1. Step 1 is we should ask ourselves which variable pair is independent or which variable pair is dependent. Let's start maybe with the right-hand plot. Here we see E and W. If you now want to see basically decide from a scatter plot whether those 2 variables are dependent or independent, you could ask yourself, is it possible to get a good prediction about W given E? And here you realize there's no good way to do this, because any value of E has basically a support for W between 0 and 10. So those probably we would say these 2 variables are independent. Whereas on the 2 left-hand plots, we would conclude or infer, we would kind of crank our statistical machinery in which is use maybe a correlation, and we would check whether this correlation is significant. For the middle plot, for example, we would find that E and S are indeed positively correlated. On the left-hand plot, if you would do a dependence test between W and S, you would realize, well, maybe they're not correlated because it's not a simple linear relationship, but somehow you can predict S from W. So let's say you observe W to be 0, then you know that S must be between kind of maybe 10 and 20. Whereas if you observe W to be 10, then you know that S cannot be anywhere between 20 and 10. It needs to be these smaller values. So you can gain some insight about S by observing W, so they are dependent. So I'll just kind of skip forward now. We have these 3 pairs of variables, and let's say we have our statistical testing machinery, and it outputted basically a significant dependency for the left two plots and no significant dependencies. So we conclude they're independent for the right-hand plot. Now we can list all possible graphs that could give rise to such dependency pattern. So this is now basically kind of a jump, and maybe you would need to take the time to list all the possible graphs. You will realize if there's 3 variables, then there's 25 possible graphs. Now I've already reduced this to 7 possible graphs, because we know if the data is governed by a functional model, then we know that also the causal Markov condition should hold. So we know that variables will be independent of their non-descendants given their parents. So you can convince yourself, if you observe this particular pattern of dependency and independency, and also you observe that each 2 variables are still dependent even if you condition on the 3rd variable, you will realize that all the other graphs that are not shown here cannot explain such a pattern. And then now it's still somewhat kind of not satisfactory, because we have these 7 graphs and we say, well, all of those are compatible with what we've seen. This is kind of the ambiguity that we have if we just consider dependencies and independencies and the Markov condition. We cannot further decide between those 7 graphs which one should be the true causal graph. It turns out, so now this is again the art of kind of causal inference and making this like an algorithmic procedure. We have now cut down the number of possible causal graphs from 25 to 7. This is already somewhat of an achievement. Now the idea is, what are assumptions and concepts or more general ideas that could make us kind of zoom in and decide, okay, it needs to be, let's say, the latter one of those 7. It turns out there's a very natural choice, namely an assumption called faithfulness, that tells kind of the converse story to the Markov condition. So the Markov condition is kind of saying, or the Reichenbach's principle, if there is a dependency, then this should be explained by a causal structure between these variables. There needs to be some cause-effect relationships that make these variables dependent. And faithfulness is kind of the inverse assumption. We will also be happy to accept if 2 variables are independent, well, then there shouldn't be a causal structure between W and E. So let's say maybe you find X and Y, again, in Reichenbach's principle, dependent, then you are happy to accept that either X causes Y causes X, or there's a 3rd variable that causes both. And now faithfulness is the converse assumption that basically says if you find X and Y to be independent, well, then there cannot be an arrow from X pointing to Y. Y cannot be an effect of X, because otherwise we would have seen a dependence between those 2 variables. This might seem at this point maybe a bit kind of cumbersome or artificial why you would need such an assumption, but you can maybe imagine for a moment the second to right graph here, and it's quite plausible maybe that there's a way. So let's say this is a linear model, E causes S and E causes W and causes S. So there's 2 paths from E to S in this graph. And now we could maybe fine tune the effect of E on to S direct, so this lower edge, and we could fine tune the upper edge via W such that the effects exactly cancel. And indeed you can show that this is possible, and then we would have the following case. Then there would be an edge between E and S, but data would not reveal a dependence between an E and S, because we have fine-tuned the parameters to exactly cancel out. And these are kind of the obscure cases that we're ruling out with the faithfulness assumption. Apart from this side note now about what this faithfulness assumption is, I want to basically recap what we've done here. Is we've started with 3 variables. We've assumed there is a causal model that explains how those 3 variables relate to one another. Then we've observed data from the observational distribution. We agreed on the Reichenbach principle, or on this Markov condition, and then we listed all graphs that are still compatible. And this is a very kind of principled algorithmic way. Like, we're not getting any free lunch here. It's still 7 graphs unless we do a further assumption. But at least we don't need to kind of do magic about what is causality and what not. We just accept that causality should induce dependencies. So this is kind of the Markov property. And if this is indeed the case, then we can go from data to causal structures. Here, unfortunately, we could only narrow it down to 7 graphs unless we make further assumptions. But the idea of this causal inference machinery is to make this a very kind of principled way. And as soon as we have agreed on the assumptions, we will all agree on the causal inferences. Then we can be wrong about these kind of fundamental assumptions, how we expect causality to turn out in real world. But we wouldn't be kind of caught into these troubles, for example, in the chocolate consumption and Nobel Prize winners example. If you only look at this correlation and you haven't agreed on any principles, how causation kind of manifests itself in observations, then people could, and as these newspapers have, you could come up with any story. For example, the geniuses eat a lot of chocolate. And for you, it would be more like a hand-wavy argument, well, this is probably not true. But here we're trying to do this on a purely kind of data-driven basis and in a very principled algorithmic way. What can we do once we have a causal model? So this will be a quick part here. So I focus more on the intuition why a causal model is something more than a statistical model. I've shown you an example of how could this causal discovery work. We've seen these 2 variable examples where we kind of looked at the scatter plots and found there are certain properties of the scatter plots that maybe tell us something about causation. Or another way is this Reichenbach's principle. So we kind of link dependencies in data to structural causal properties. But now let's say, okay, we found a causal model. We know data is generated by this causal model. Then what we can do with a do operator is quite cool. We can write, of course, down the joint distribution, which is just the factorization according to the graph. But we can now replace any of those conditionals xi given the parents of xi by a point mass. And this will give us, so this you see on the left-hand side, this will give us the distribution of x1 up to xn, given we have intervened on xi and set it to the value xi star. So this is, if you think back about this, to this very simple 2-variable example, this replacement of equations is exactly what you need to do to obtain all interventional distributions. So once you have a causal model, you can talk about all interventional distributions in a systematic way. You can kind of just follow the rule book how to derive these interventional distributions. Why is this cool? And here's maybe 3 examples. So these examples are exactly the ones that we've seen in Reichenbach's principle also. And then we can ask ourselves, so if X causes Y, what happens if we intervene on X? And then there's rules for this do calculus basically that tell you if X is a cause of Y, then the probability of Y given you set variable X to a certain value is exactly the same than just observing Y given X. Whereas if you now jump to the 3rd bullet point here, if X is an effect of Y, then Y doesn't change once you intervene on X. And this is something that will just fall out of the do calculus rules. You will realize that Y given do X equals the probability of Y. So intervening on X doesn't change the probability of Y, which if you look at this causal graph is kind of intuitive because you're just intervening on something downstream of Y. This wouldn't affect your probability of observing Y. And then on the 2nd bullet point, you can again kind of crank this do calculus machinery and obtain the same statement that intervening on X wouldn't change anything about the distribution of Y. So this is how you can use now this causal model and this do calculus and do operator to reason about what happens under intervention. One very cool application of this is confounder correction. If we know this to be the true causal graph, we know that the distribution of Y given X is not the same as the distribution of Y given we have intervened on X, because we have this confounding variable set that also induces some dependency between X and Y. But with the do calculus, we know exactly how to compute both the left-hand side. So we know how to compute what happens to variable Y once we intervene on X. And we also know how to, of course, to compute the conditional probability. And we can see that they're not different because they differ in this factor here, P of Z or P of Z given X. So this maybe is a bit quick now, but you can convince yourself that this is just something that falls out of this do calculus. It's once you have your causal model, you really only need to follow these rules. I want to give you an example of why this is cool. This is again taken from Pearl, and it's one historic example. It's smoking and cancer, and here he kind of wants to illustrate how this is a very useful tool to have this notion now of conditional probabilities versus interventional probabilities. So let's say in 1964, the suspicion was that smoking causes cancer. So now we have smoking and points an arrow to cancer. If this is the case, we know that then intervening on S, so making people smoke, will result in higher probabilities of them developing cancer later on. Or if we prohibit smoking, then hopefully we will reduce the probability of them developing cancer. This was a bad suspicion because the tobacco industry wanted to sell tobacco. So they came up with a quite clever counter argument. They said, well, it's not actually the smoking that causes cancer. So basically what they put forward is this alternative causal explanation for the dependency between smoking and cancer. And they invented a genotype argument. They said, well, there is some gene, there's certain people, certain types of people that tend to smoke more. And unfortunately, exactly those people who tend to smoke more will also be the people who tend to develop cancer more often. A priori, there's no way for you to distinguish between the two explanations because we only observe smoking and cancer and had no way of accessing genotype. And by Reichenbach's principle, we know, having observed the dependency between smoking and cancer, there could be three possible explanations for this dependency. And basically the tobacco industry just choose one that is very good for kind of selling your tobacco because smoking is not actually causing cancer. You can just happily keep smoking. Now that we've kind of developed this machinery in toolbox and we know how to reason in causal models and in causal modeling, we can take this a step forward and we can say, well, okay, if we cannot decide between the confounding effect of this genotype and the direct effect of smoking on cancer, maybe there's something we can do. And it turns out oops, I'm jumping back. It turns out if you have a causal model where there is this genotype that we can observe, but there is smoking causing tar causes cancer, then we can indeed compute the effect of changing the smoking behavior on cancer. So if we now can measure tar on the lungs, which we then did basically, we can exactly compute what is the probability of cancer making people smoke, given we make people smoke, or what is the probability of developing cancer once we make people stop smoke. And this is true even if there's a hidden confounder. So it follows by mathematical arguments. If we know this tar, we can compute probability of cancer development given we make an intervention on smoking, which we cannot if we don't observe this node in between smoking and cancer. But if we do, we can compute this. And then of course we can decide the battle basically between tobacco industry and health experts, because we can compute this and say, well, indeed, we found as you do increase smoking, you do increase the probability of cancer. And this is a very cool way to apply this kind of causal modeling and do calculus machinery. I'm just showing this for reference basically, but what I wanted to take you away here is this is the rule how you can derive the interventional probability of developing cancer given you intervene on the smoking behavior. And then you see a 7-step procedure here, how to derive this statement purely in terms of, and this is what you need to focus on here is the bottom line. This is now only purely in terms of observational quantities. There's no do any longer because we won't probably induce and force people to smoke. So we couldn't run this experiment, but we can observe, of course. And if we manage to rewrite this quantity that we're interested in, just by following rules, we can now represent this as observational probabilities. Then we've exactly succeeded and we can settle the debate between the tobacco industry and the health experts, just following this very kind of algorithmic axiomatized framework. Okay, I think I'm running a bit late, so I'll briefly summarize what is on this slide. Is basically what is also called the ladder of causation. On the left, you see level 1, level 2, level 3. We've mostly talked about level 2 today. So I wanted to convince you that beyond associations, there is something to be talked about, which we call interventional distributions. And a causal model models observational and interventional distributions. And it tells us how the system changes once we intervene and set a certain variable to a certain value. There's also another level on top of this causal reasoning. We could also ask counterfactual questions that are kind of retrospective questions. So let's say you don't have a headache any longer. Now you can ask yourself, well, had I not taken the aspirin yesterday, would I still have and suffer from headache now, or wouldn't I suffer from headache now? It's a bit different from this interventional question, and it would require you even stronger kind of assumptions to make inferences about counterfactual statements from observed data. But for now, I want you to mainly take away this interventional level of causation. This is from a 2019 paper, and there was also accompanying NeurIPS challenge. So 2019, there was a causality challenge at NeurIPS related to climate and kind of weather phenomena. And this slide is to illustrate there's of course many open problems, and is an interesting research area because you can work on any of those, and it's an advancement if you achieve any nice solution to these problems, because causality is indeed a hard, tough challenge to solve. And you can see here, like if you now talk about inferring causality for very complex systems from data, you run into, I mean, this is kind of here categorized into 17 different problems. There is autocorrelation, there's time delays. You could have a problem of unobserved variables, which we haven't talked about. You could maybe not sample your observations at fine enough intervals. Maybe the sample size is too low. Maybe it's just a very high dimensionality. So all of those kind of problems on top still persist, but at least we have a very principled way of how to agree on what is a valid causal inference given a certain input data. So quick recap, causal questions require causal answers. It's absolutely fine for many of those tools maybe that we're developing with astonishing success in machine learning. For some of those questions, we don't actually ask a causal question. If you want to detect faces on an image, it's not a causal question. You can feed in training samples to your machine learning algorithm. And if it succeeds in recognizing faces, then this is all you care about. But if you want to predict what happens if you change something about the world, this is a causal question. You will need a causal answer. Unfortunately, in this sense, the slogan is still true. Correlation does not per se imply causation, and you will need to make further assumptions to make this work, and then correlation may tell you something. And this is what causal inference is about. It's kind of making this leap instead of just stopping at, okay, we cannot say anything about those interventional distributions. We will kind of distill certain core assumptions and principles that will allow us to make this inference. With this, I want to conclude. I think there will be time also for questions on Slido, but on this finishing slide, I want to repeat and hint you to those further lectures on causality. And also on Wednesday, there will be a session on causality where you will learn most of this in more detail than what I've covered here in this 1 hour talk. So this was it from my side. I hope to have convinced you that causality is interesting, but causality is very hard. And it's an intriguing research topic. So I want to encourage you, whenever you do machine learning, keep this question kind of at the back of your head. Like, is there something to be gained by employing this type of causal reasonings? And I will now switch also to the Slido, and you can ask me questions via Slido. All right, I hope you can still all see my screen. So on the left, I will have my slides for reference if I need those to answer any of the questions. And now I can maybe go ahead and answer some of the questions. So the first question is, should you use the regression t-test when you want to check if the factor actually affects the output? So a t-test itself won't kind of allow you to distinguish between correlation and causation, but what you can use the t-test for is, so maybe let's go back to the slide for Reichenbach's principle. That is here. So Reichenbach's principle says if two variables are statistically dependent. So what we now use the t-test for is to decide on this statistical statement here, namely a dependence between two variables. This is a purely statistical property that we're talking about here. And for this, you can use indeed use a t-test, for example. You can regress x on y, or you can regress y on x. And then you can ask yourself whether there's a significant correlation, so a linear dependency between x and y. We've also seen an example in this wind speed bike example where there was a nonlinear relationship. Then maybe you would need to use a nonlinear dependence test. So you would maybe use the Hilbert-Schmidt independence criterion, for example. So basically, you can use any statistical tool to decide on these dependencies. And this is what the statistical machinery is very good at. But then to go and move forward to do a causation, a statement about causation, you will need to employ some further assumptions. One of them is Reichenbach's principle, for example. And it will tell you, once you've looked at the result of your t-test, it will tell you, okay, one of the three graphs is now the causal graph, but I cannot decide any further between the three unless we do some further analyses. I hope that answers, I think, the first question that was highly upvoted by Olga. Then I'm gonna continue with the second question. Any words of wisdom for data science students or practitioners starting out? Well, this is a very general question. I think my number one tip would be don't stop asking questions. So if like there's many great tools that we have nowadays in data science and machine learning, but there's so many ways results or cool performance can come into place. And especially if you want to kind of use a tool in practice, so by which I mean maybe you're running a predictive machine learning model to predict maintenance times. If you fall wrong, if you basically kind of forgot about certain other ways how your model performance on your training data could come into place, then you will be highly misled in practice and will run kind of off. For this kind of, I think, in general, the wisdom is just keep asking, is there any other explanation how this could have happened here? And if it's more about data science students and how you get kind of the up to speed with data science, I think is now a great era and a great time. Everything is online, such as, for example, this summer school. So use all of those, just keep an open mind and go where you find it the most interesting. Okay, I'm gonna jump now to the first question. There's a new top rank question. I guess it might not be possible to acknowledge all the causal factors. There must be some hidden factors which do affect the output. How to model such scenario? Yes, this is a very good question, and indeed is a very strong assumption to, so in the example that I've shown here in this lecture, I assumed we've observed all the factors. This is also called causal sufficiency. It turns out you don't have to make this assumption, and there's ways where you can even allow for hidden variables. So by which I mean you can accept the fact that there might be hidden variables. And then there's the principled way that tells you for certain cases you might still be able to rule out certain causal structures. So it gets, of course, a tougher problem if you assume there might be hidden variables affecting your observed variables, but you can still do something by just following these rules basically and asking yourself, what would a hidden variable induce for a dependency structure in my observed variables? So it will be a tougher problem, but it's not unfeasible. And indeed, like many of the kind of, if I may say, like off-the-shelf causality toolboxes, they usually allow for hidden confounding variables. So this is it's not unsolvable. It's just not, I basically didn't present this procedure here, but it's possible to allow for hidden confounders, and you don't have to observe all of them. But for this, you need to be kind of happy enough to end up in a situation where you can still infer something about causality. If you're really unlucky and let's say you have one hidden variable that affects all of your observables, then this could explain all sorts of dependency patterns. Then it will be very tough to infer something about causality. And I encourage you, if some of the answers were not satisfying, just repost or maybe slightly rephrase and bump it up again if I should answer to any of those questions again. How can you get experience in data science without a job? There's, I would say, the go-to data science competition website is Kaggle. I think this is a very good idea to get started on kind of hands down implementation and running your models and algorithms and getting some first predictive results. If you're more interested in getting up to speed with the theory behind data science or machine learning in general, then I think I would actually start with the machine learning summer schools or data science summer schools that you find online. Is Granger causality a nice interpretation or solution causality? I think Granger causality is actually, it's very good that you bring this question up. So Granger causality is kind of, when I talk about Granger causality, I'm always kind of a bit torn apart because it often gets misrepresented and misapplied. And this is why maybe it's not kind of, it's not very, there's no safeguard mechanism. It's often, there's many Granger causality toolboxes that you can just apply off the shelf. They will produce some output and it will maybe lure you into the idea of, okay, I've now inferred something about causality. If you read the original paper by Granger, which I highly encourage you to do, you will realize that he was very, very careful in how he phrased his notion of causality. And I think in one paper, he even said, well, you should call it G causality because it's this particular type of causality. And then everyone knows you're talking about my set of assumptions. The main problem with Granger causality is often, so basically the definition of what it means to be a Granger cause, so for X to be a Granger cause of Y, it involves, if you read the original paper, it involves something that Granger calls all information in the universe. And this exactly refers back to the question that we just had about hidden variables. There's often hidden variables and factors that we cannot include in our model because we simply cannot observe those. So it's basically saying if you do Granger causality and you don't make up your mind about whether you have observed everything relevant to your system, then you fall into the same kind of problems and troubles where you cannot account for all hiddens, and then your inferences will be wrong. If you're talking about a very well understood closed setup and you can kind of very plausibly make the assumption, okay, I've definitely observed all factors that are relevant for this particular phenomena, then indeed Granger causality is a good tool to get some information and some inference about which variables cause what other variables. And I think it's fine, but taken to be with caution and be very careful about the assumptions that actually underlie the causal, Granger causal machinery. I'm gonna jump to the next question. How to deal with something, oh, sorry, now it jumped. Okay, I'll still do the second one first. How to deal with something like games fallacy. If in a data stream you prefer the recent inputs, then the distribution becomes good. I'm not quite sure I understand the question. If the question is about changing environment, so you kind of learn online and you do something and then the distribution changes, it will basically mean your inference will be very difficult to do because you need to take into account all the previous interventions that you have performed. But maybe otherwise just repost and I will clarify as much as I can. Then now back to the first question. For all causal models, can we say all these distributions form a single surface where we move from one distribution to another? I think I would basically only advocate this image as an intuition for you to think about what a causal model is. For some, let's say you have this linear structural causal model, you can at least you can indeed kind of smoothly move along certain kind of subspaces in your probability space just by changing the slopes in your, like your linear coefficients. But for other models, you might not have this kind of smoothness idea here. And what will still be true is that you write down a set of equations and you change the parameters, you will change all distributions at the same time. Not only the observational one, but the interventional ones will also be affected if you change certain coefficients or functions in your structural causal model. Then I'm gonna jump to the next question by Nikita. Amazing stuff. Is there already any progress on automated learning that use the causal machinery? There is definitely toolboxes out that do some of this basically just automatically for you. I think recently there's also kind of ideas where you could use smooth optimization in a very clever way. This is for the ones who want to read up on this. You basically need to search for DAGs with no tiers, which allows you to optimize over acyclic structures over smooth optimization problems. So there's some stuff out there. I think off the shelf, you would probably use something that is called greedy equivalence search, so GES. This is an algorithm you can just use on your data set. There's also fast causal inference, FCI algorithm, and there's implementations of this out there. What is maybe a question that deserves more attention is, how would you, so when you say automated learning, there's of course, one thing is to start from a given data set and then run this through an automated pipeline to give you some causal inference at the end. But another question could be, okay, how do you design further experiments? So let's say you want to automatically decide, okay, what is the next variable that I should intervene upon to learn more about my causal structure between variables? And this, I think, is kind of a merger and somewhere between active learning and causal inference. And I think this is a underexplored field so far, where I think there's great hopes that this could actually be a very fruitful approach and guide us more towards kind of even reinforcement learning settings where you know a bunch of stuff already, and then you try to find the most informative next interventional experiment to run. Can I share a link to the paper? I will share references, I think, either on my website or Twitter announcement, and also maybe on the Slack channel. You're of course free to ask for references and pointer, but I can definitely provide those, yes. Where can you learn about causality more? So beyond the lectures that I have listed on the slides, so this will again be kind of online lectures. I think there's probably 2 or 3 references that I would suggest as a starter. One is a primer on causality by Julia Pearl. I can also provide the reference in one of the platforms that I will kind of post also the slides. And then there is a very good book by Jonas Peters, Dominik Jansing, and Bernhard Schürkopf on causality that is also has like dedicated sections for machine learning and causality. So I think it's a very good starting point if you're coming from a data science, machine learning background. This is, I think, a go-to start where I would dig into and start reading. I think this answers hopefully Sarah's and Jaroslav's question about kind of written literature on how you could read up on causality. I think I will post the links to those few references after the lecture. Yeah, do calculus. I think it's the same topic. I think so. Definitely, Pearl's book is kind of is one of the go-to references, and then is one by Spiritus, Glimmer and Shines that you should also, I think, kind of take into account for kind of standard references books for these ideas. Could you provide examples of using Markov's chains for real projects? I know that Google is working on it. What else? I'm not quite sure what I can say about this question. For the real projects, I think basically Markov chains are I would probably think you would find this most interesting in connection with the Granger causality ideas, where you have a time series development and then Markov assumptions basically along Markov chains are telling you which time steps should be independent of others, given you have observed time step t already. I'm not sure. I'm sorry, I cannot give a good answer to this right now, I think. Can this causal framework be used for the systems which contain feedback loops? Feedback loops is a very good question. Is also kind of a bit of a, maybe not open debate, but there's kind of different takes on how you should deal and think about feedback loops in causal models. One answer that I quite like is that often feedback loops may be thought of as arising from, instead of viewing a system as developing over time, you view it as a kind of time agnostic model. So let's say we do believe that X at time point t causes Y at time point t plus 1. And we also think that Y at time point t causes X at time point t plus 1. But the way I've just phrased it, it will just be forward in time. So X will cause Y forward in time and Y will cause X forward in time. And there will be no feedback loop in this sense. If we model this as a time evolving system. If we now collapse this and talk about this as X causes Y and Y causes X, we will have a cyclic causal model. And there's much work on this right now, and basically recent years, how we can talk reasonably about and do inferences about cyclic causal models. So I think feedback loops is conceptually very interesting problem, and there's much work on this. So it can be dealt with, but the classical kind of canonical assumptions start usually with an acyclic, so a causal model without feedback loops. How does it relate to probabilistic graphical models? I think is probably one of the last questions I'll take. So I think for this, I'm probably gonna jump back to this slide here where I have these two models. So on the left, you see a normal probabilistic model. On the right-hand side, you see what I call a causal model. And a probabilistic graphical model is, it basically lives up without further kind of specification. It lives on the left-hand side of this plot. It's a classical probabilistic model. It's a probabilistic graphical model. So you draw nodes and you connect them with arrows and you decide on the conditional and the Markov kernels between those nodes basically, and it will induce a distribution over all variables. And then you can also reason about conditional distributions in this graphical model. The question now is, can you also interpret this in a causal sense? Well, obviously we often even draw a graph if we do causal modeling. But from a graphical modeling perspective, for example, now I'm jumping to this slide, the three graphs shown on top, they're all classical probabilistic graphical models, and they all induce the same observational distribution. So they're indistinguishable based on the observational distribution. They only become different once we care about causation. And now a graphical model is now a representation for a causal model. But if we intervene, we will basically, for example, remove any incoming edges for these variables that we intervene upon, and then we will obtain a new graphical model. And whether this then indeed truthfully models the interventional distribution, this is a different question for which we need to employ these causal assumptions and causal inference machineries. I'm not sure how pressed we are on time, but I'm also happy to answer some more questions. So that's up to you, I guess.
Yeah, thank you, Sebastian. Thank you so much for this intense talk, and really heavy loaded with all this pretty new information, I believe, for most of us. This exciting topic, and I believe you encouraged people to join Margarita's course for more details, and I believe you guys can ask questions to Margarita as well. So Sebastian, thank you once again for answering the questions in such a detail. And if you don't mind, please continue chatting with the participants in Slack. So guys, if you have new questions or you feel that your question was unanswered, just jump to Slack and continue talking to Sebastian. So Sebastian, thank you so much for joining us. It was a great pleasure, and I hope next summer, there will be no obstacles to have you here in Lviv, and we can have you here in live. Thank you so much.
Thank you so much. Take care, everyone. Thanks.
Bye.